It's always interesting when you come to these events just to listen to the comments of other people on the panel, and it does give you an indication as if, from a manufacturer's point of view, whether you're heading along the right way. What I've actually done is prepared a simple and short sort of case study, if you like, and a real-life example of a district heating scheme. Armstrong themselves are specialist in pumping solutions, so when we were talking about transporting that heat from the energy centres around the underground network and then obviously into the building themselves, we can make that interaction between the energy centre and the building. So the project that I've chosen is one that we probably got as much out of from a partnership side of view, working with one of our trusted clients, which is Vital Energy, as we did from the technology that we developed off the back of it. So the scheme itself was in Greenwich in London, and it was a redevelopment of some wasteland really close to the DLR station over there. The site itself, just to give you the stats, covered 181 new luxury homes. Included within this as well, there were 358 student apartments. There was a 104 bedroom hotel. There was about 7,000 square feet of industrial units for sort of incubation and startup businesses, as well as the sort of gym and leisure facilities that you get, along with the various cafes and nurseries and all that kind of stuff that goes with these new developments. And included within that was an extension to an existing sort of community centre that was already on site. The energy centre itself, I believe, is round about the 6 megawatt mark, with a biomass plant in there. And Vital Energy were awarded the design and build contract for the biomass energy centre, as well as a contract for the installing the district heating network. And probably more importantly for them, this was their first time operating as an ESCO, so they had a 35-year commitment to this project as well going forward. And obviously that starts then to put the pressure on the supply chain of which we sit in. The project itself was started in 2012 and I believe was commissioned and finished in about September 2014. So, as I mentioned, there were quite a lot of challenges on this, and as always with these type of projects, there are benefits for all parties. So yes, Armstrong themselves, we wanted to get some benefit out of this that we could take forward. Vital obviously had their input into it, and then there's a client and the end users that want to get theirs. So just taking the ones that were probably important to Armstrong first, whatever solution that we had to be repeatable. We have a standard range of products, we wanted to try and use those as much as we can. The development that we did out of the back of this, we wanted to be able to use on follow-on projects. It would be brilliant if we could make it scalable and have a common solution that we could put in, which was a vital model, if you like, to go forward with that particular client. The solution itself needed to give some level of flexibility, so we couldn't just command to people that you use this box and it will deliver all of your savings and all of your problems. So that was the one from us. When you start to think about what Vital's commitment was to it, items such as the life cycle of that plant, its 35-year commitment, whether it could be maintained, what the uptime was, and whether we matched a particular type of resiliency, so they didn't get any penalties throughout the lifespan of the building. Size of the footprint, maybe not quite as important to us. We can make them as big as possible. But if you're trying to squeeze some equipment into a quite confined space, and what you've got to think about is when you are building a new city or a new development, you've got to, you want to try and maximise the rental space on that, or the living space. The last thing you want to do is give some of that precious space and area up to plant space. So to make the solution and the installation as small as possible is obviously quite important from that point of view as well. The other touch points I want to take here is energy usage, and I think it's one of the things that Rebecca mentioned right at the beginning, was, yes, we're not involved in producing heat or producing energy, but we transport that heat from one place to another. And every little bit that we can do, I think the figure quoted was sort of 6 billion or something like that. Even if we make a small inroad, 0.5%, 0.25% on starting to reduce that figure, is quite big numbers. So the energy usage that we could do and the technologies that we could put in place to reduce that would certainly help us along. Specialists in pumps, so again from our point of view, pump selection and the control strategy that we could bring into it and bring into the pot was quite important for us as well. And again, this sort of goes into the repeatability aspect of it. Once we've designed a control strategy, can it be repeatable and can we roll it out onto other buildings? So, as I mentioned, the benefits of this project were twofold. Yes, to us as a manufacturer and a product development point of view, but as a collaboration, if you like, between ourselves and Vital. We have quite a good relationship with Vital, which is essential to the way that we develop this project. What that enabled us to do was get some very, very early engagement on the energy consumption profile for that particular development. And it might not seem so important when you're talking about a small component within a big scheme, but it absolutely is. And taking Lars's point about controlling return temperatures and that people talk about flow, I think about flow, I pump flow around systems, but he's absolutely correct. You know, we need to manage the differential temperatures within that system so that we're always returning at a point where we can get the maximum efficiency out of the boilers and the follow-on plant. Traditionally, what we would do within this kind of building to add some resiliency is we'd do what we call a 3-pump set. So we'd split the 100% duty in flow between 2 pumps, so each pump can do 50% flow. If one fails, we've got a 3rd pump in place. Just looking at that graph, if I had 2 pumps that delivered 50% each, what you can actually see is those pumps are most efficient when they're delivering full flow. So your peak efficiency points on your pumping solution would be 50% and 100%. That graph actually shows how many hours that plant will be running at those particular points. So it's quite a compelling argument to say that the pump selections in a traditional manner would be wrong. So what we actually did was start to put some clever strategy in place to do that. The second point that we talked about was on the reduction of the footprint itself, and the drawing on the right-hand side, hopefully you can see it, but if not, don't worry about it. The traditional installation capacity for doing this would be to take things like inertia bases and put a mass of concrete in there. From an environmental point of view, do you really want to be adding concrete into a building when you don't want to do it? There's additional pipe work in there, so we wanted to look at a solution that would help ease that and reduce that input as well. So what we actually did was start to look at that energy usage profile, and we got a little bit creative between ourselves and Vital, and we said, well, why do those pumps need to be the same size? Why don't we look at the efficiency bands? Why don't we look at developing a solution that delivers pumping efficiency at high efficiencies at 20% load, which is what we did. And the solution that we actually came to was that we started to put unequal size pumps onto a system. And then we obviously had to control those. So there's a control strategy that had to sit behind that now didn't just look at pump 1 comes in, ramps up to a speed, pump 2 comes in. It's now selecting which pump runs to deliver the best efficiency for the building load. So we created that as a standard and repeatable package, and we did that going forward. One of the algorithms that we added in there was parallel pumping. So we can now run 2 pumps, 3 pumps together at the same point. What we actually do is we take intelligence out of the motor drives that have power meters in there that can constantly tell us the amount of power consumption for the motor and the pump as such. We can relate that back to a flow rate for the pump, and we can relate that, more importantly, back to what the efficiency of that pump is. And it's always assessing these particular parameters to make sure that the correct number of pumps are running at the correct speed to deliver the best efficiency for that particular piece of plant. And one final technology that we employed in this that we already had was the actual speed control of the pumps. Traditionally, you'd have sensors out in the field, which on large networks can be quite difficult to locate. Just actually finding out where you're going to put them to give you the best efficiency turn down for your pumps is difficult. Then you've got the cables and the networks that go with that. The technology that we had in place uses the power meters and the power sensors within the pumps to dictate any changes out in the system and then reduce the speed of those pumps respectively without the use of sensors themselves. So what that meant was that when we come to do the install, everything gets quite easy because there's no other plumbing and wiring that needed to go into the device itself. So Armstrong as a business, we cover pretty much all the touch points on district energy circuits. We can do everything from the heat substations to right out into the district community. But in this particular project with Vital, we were concentrating on the pumping solution within the energy station. So what we actually developed was an IFMS, an integrated flow management system. If anybody wants to know what one looks like, we've actually got one on our stand, which is right where the food's going to be delivered later. You can't miss it. It's big and it's red. It took us ages to get into the building, so we'd love you to come over and have a chat to us, even if you just want to know how we got it there. The benefits that delivered, not only to us and to Vital, was, I guess, the nice simple ones. We limited the inertia bases for the system, so low vibration pumps. We're removing concrete out of a building straight away, and the environmental impact of that is useful going forward. Reduced the amount of steel because we squoze the footprint in as well. What we also did was employed our pumping strategies in there, so we've got parallel pumping strategy with best efficiency staging, so we're always maximising what we can do with what we've got. We minimise the space, so again, you know, you may have more lettable space now, or you can build an extra building or something like that, which is good. One of the benefits of using the unequal pumps, and again, Laird's touched on it about bypassing flow around buildings. Why would you do that? There is a reason why you have to do that at a certain level, is if you want to run a pump at all, it has to deliver a certain amount of flow. The smaller the pump, the less flow you have to deliver. And what that allowed us to do was reduce the size of that bypass flow. So again, just simple technologies that are already in place and a different way of thinking using what you've already got is improving your overall situation. We had a control panel on there that was embedded and pre-programmed, and we did that within our factory in Hales Owen. And the system's essentially plug and play. Again, if you come and have a look at it on the stand, what you can see is there's 2 water connections to make, so 2 big manifolds. Because we had embedded power on it and motive power, you basically bring your power cable in and plug that in, and you plug your cable into your BMS. Commissioning is nice and easy and done from the control panel itself. Just one final slide, just to prove that it is repeatable, and obviously, you know, Vital took this on board as well, and we've done quite a lot of work with those going forward. Those are the sort of sites that we've employed this technology at up to press. I guess the 2 relevant ones for where we are at the moment is the Hill of Bankery up in Aberdeenshire, and the Commonwealth Games was done in 2014. Quite a particularly interesting case for the Commonwealth Games, because when you start to look at, and I started talking about energy usage right at the beginning, and how you've actually got to assess what the usage is going to be over time, with something like a Games, and it would have been the same with the Olympic Games, you've not only got the Games mode to worry about, you've got what happens after that from a legacy point of view. And just finally, I work for a manufacturer. We can only develop products if we challenge and there's a market for it. So my challenge to you is to challenge us. We can only push forward if you do. Thank you.